Hello. Today we're going to look at 1.2 and 1.3 more on functions. So in this particular section of 1.3, we look at what makes a function even and odd. We also look at the symmetry. Then we discuss increasing, decreasing, and constant intervals. And last but not least, one thing that's going to be your favorite is the difference quotient. And in 1.2, the only thing that we have in this section from 1.2 is just a review of domain and range. I thought we might need some extra help on that. Okay, just recall that when you're doing domain and range, that if you have an open hole, you use parentheses. It means that the graph does not extend beyond that point and does not belong on that graph. Of course, an arrow indicates it extends infinitely or indefinitely in that direction, and a closed dot indicates that the graph does not extend beyond that point and does not belong on the graph. Okay, just to review, identify the function's domain and range from the graph and find f of 4. So once again, we talked about in that last video from 1.2, domain just indicates how far left the graph goes and how far right it goes in relation to your x-axis. So if we're looking to see how far left this graph goes, it goes to -1. Notice there is an open hole at -1, so it has parenthesis, bracket, -1. Notice that it goes to the right to 4, but it is shaded in at 4, so you do 4 and then bracket. And once again, this is called interval notation. Your range, how far down the graph goes in relation to the y-axis, and you always do it from bottom up. So this graph goes down in relation to the y-axis to 1, and it's closed in, so that's why we have bracket 1. Then it goes up to 3, open hole, and that's why 3 has a parenthesis. Looking at this graph, domain, how far right does your graph go? So we're following the graph, left. It goes left to +2, shaded in. Left to +3, shaded in, so bracket 3. Notice that it's going to the right, infinitely. So infinity, and recall, always put parentheses around negative infinity or infinity. And range, how far down does the graph go in relation to the y-axis? It goes down to 0. And then it's going up, 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 and to the right forever, so infinity. Okay, for this particular example, let's go back. I forgot to do f of 4. All right, for f of 4 in each case, once again, they're giving you the x value. F of an x value is equal to the y. So you're trying to figure out what y value corresponds to x value of 4 on this graph. So let's go to x-axis at 4, go up to where your graph is at, and the y value corresponding to that is 1 in this case. F of 4 in this case, go to 4 on your x-axis, go to your graph, follow to your y-axis, and you see that's a value of 1. So in this case, it is also 1. All right, in this particular graph, identify domain and range. Domain, your graph is going to the left infinitely. So we use a parenthesis, negative infinity. Your graph is going to the right to 3 in relation to the x-axis, and it's closed in. So remember, use a parenthesis around values that are not particularly on your graph, but that may approach or touch it, but it's not actually at that value. Range, how far down does your graph go in relation to the y-axis? Notice that the graph goes down to 0, and it is filled in. So we use a bracket. And then it's going up, 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 and to the left forever. So infinity. And the value of f of 3, find 3. This is your x, recall. So we're going to find 3 on the x-axis. And notice that you actually have a point on the graph at 3, so your y value is 0. And then you have an x value of negative 1. And go to negative 1 on the x-axis, go up to your graph. Your corresponding y is 2. I'm going to change it up a little bit. Recall that you had some problems in your homework that said find f of x when your y value is, we'll say 3 in this case. So what they're giving you here, they're actually giving you your y. So you would start on your y-axis first, and then find the matching x that's on your graph. And then you're finding x. So I'm going to start on the y-axis at 3, and then you actually have to go left or right. You can't go down to your graph, so be careful. So I'm going to go left. I see it crosses my graph here. The corresponding x value is negative 6. And once again, I told you, you could just double check. Make sure that that point or order paired, negative 6, 3, is on your graph. Negative 6, 3, it is. Here's just another one really quick. If you need some more help with domain and range, domain is going to the left at negative 4, and it's shaded in. And it stops, and there's no gaps in the middle to 3, and it's an open hole, so put parenthesis. Range, how far down does it go? It bottoms out at negative 2, and this point is on your graph, so we put a bracket around it. And then it's going, the graph comes up, up, up. The highest point on your graph is 2, and it's shaded in. And then find f of 3. I want you guys to notice when you go to your x on the x-axis at 3, the graph is actually approaching that value. Notice that you have a closed-in hole. So there is actually not an ordered pair that has 3 of an x coordinate and y on your graph. So you would say, like, no value. You wouldn't say 0. Make sure you do not say 0. You can say no value, the empty set, or no solution, or does not exist. Any of those. There's not a value. It's open. There's no y value. And then f of negative 2. Go to your x axis at negative 2 and go up or down to find your y. So we're going to go down to where the graph is. The corresponding y value is negative 2. Okay, for this example, we're just reviewing how to find the y-intercept and find f of 2. So finding your y-intercept, note that this graph, if you recall from Algebra 2 Trig, is called the greatest integer function. You don't particularly need to know that. I'm just telling you what it's called, a step function or greatest integer function. For our purposes, we need to know how to pick out information about the graph. X-intercepts, y-intercepts, domain, range, so on. So find the y-intercept. Where does this graph, any part of it, cross the y-axis? So if you'll notice here, you've got 2 points on the y-axis. However, one of them is open. So this particular piece of the graph actually does not touch the y-axis nor cross it. It actually crosses here at this point of 2. And so recall, always write x-intercepts, y-intercepts as ordered pairs. Your x value, of course, would be 0, y value 2. Then we're also asked to find f of 2. Once again, they give you, this is your x value. So go to the x-axis at 2, and then you either go up or down depending on where your graph is. So I'm going to go up. Once again, notice that this is open, meaning that that point is actually not on your graph. But notice that there is a fill-in point that has an x value of 2 and a corresponding y value of 3. So f of 2 is 3. All right, the next thing that we're going to talk about is increasing, decreasing, and constant values. Okay, so let's say that we've got this graph, and I ask you to find out where increasing, decreasing, constant intervals are. So these are all intervals. Very, very important that you remember intervals only use parentheses. And I know we just got through looking at domain and range in 1.2, and we just did a brief study of it. But intervals only use parentheses. I cannot stress this enough. I see students make so many mistakes on this every year. Intervals only use parentheses. And say it with me, intervals only use parentheses. So if we're looking at where your graph might be increasing, where it might be decreasing. Increasing is simply where it changes from a down to upward, a down to up direction. Or in other words, it changes from decreasing. So it's the point at where a graph, or it's changing from down to up direction. So let's imagine that we're on a roller coaster here. And this is the main drop, and it's dropping you, let's say you come over this hill, and all of a sudden you are flying down that first hill. And then you are actually increasing here. So when you bottom out, as you're going up that first hill in that roller coaster, or even the second hill in this case, that would be an increasing part of your graph. And then when you top that hill and actually are going down, try to let that be common sense to you. Down, if I'm going down the hill, and I know this is going to sound elementary to you, but this helps some people. Like, always draw a stick figure on top of your graph on the top, and think, is my person, are they walking flat? That's the constant rate. Are they walking downhill on this part? Notice how you've got all these points that I will highlight for you. You've got this point. This part of your graph is going up forever. So it's never going to come back, or it's just going to keep going up. And then you've got this point, that's a changing point. This point, that's a changing point. And then this one. So notice how all these points, your graph kind of changes direction at that point. And then it's either going up, down, or it stays flat. So once again, let's say that, we were dropped here, and this is your first point where you change direction. This point changes you from going down a hill to up the hill. So when you're going up the hill, that is an increasing interval. But the only part of your graph where you're going up is this part. And, well, the only part here in this case. Then it tops out, so this is another changing point on your graph, and then it changes you to going downhill. And so this would be a decreasing interval on your graph. You're going to have multiple. Sometimes you may not have any. Sometimes you may have only an increasing part and not a decreasing. That would be if you had a linear function, a line that's just continuously going up. But and then sometimes, if you had just a horizontal line graph, that would be only a constant, because it would never be going downhill and it would never be going uphill. Here's another changing point. So this changes you from going down to now you're going back up. So this part would be an increasing interval on your graph. This part, of course, any flat part on your graph is definitely going to be constant. And the reason is, let's think about if we were looking at a speed graph, and all of a sudden you stop at a stop sign for a certain amount of time. Then that part of your graph would be flat because you're not accelerating, you don't have any speed. Okay, so I'm going to draw this graph a little bit better for you. A little bit bigger so you can hopefully see it a little bit better. And I'm just making this graph up, kind of using this one as an example. This is very similar to what yours will look like in your homework. Okay. Let's pick out any increasing intervals on this graph, any decreasing. and any constant intervals. Once again, if I were you, I would maybe just circle all of my changing points where like points on this graph where it changes direction, like where it maybe bottoms out and then all of a sudden it's going downhill. Like, for example, look at this point. This is not a point where it actually changes direction. Like, coming into this point, it still keeps going down. Same thing with this point. It still keeps going down. And you read a graph from left to right to help you get increasing, decreasing interval. Read it from left to right. And I know that this arrow is going up. All that indicates is that this part of your graph is going up forever. But if I'm actually reading it left to right, I would actually look at this part as, well, it's going downhill, so that's a decreasing part. So from here to here, that is a decreasing part, and that's where it changes direction. So then, and we only use very, very, very important, you only use X values. We are never, ever using Y values. So only use X values when you are listing increasing, decreasing, constant. And we only use parentheses, which we've already written that, but very important. Okay, so I know that I've got that is actually a decreasing interval. Okay. Decreasing interval there. This one is decreasing to that point. Then at this changing point, your graph starts going back up. This is a changing point here. This is this. Remember, a changing point is just where does it change actual direction. Then it starts going back down from here to here. Starts going back uphill from here to here. And if you're like me, I absolutely love roller coasters, and that's what this kind of reminds me of. And constant. Of course, any flat part of your graph, so it's constant from there to there. And at that point. Now, to actually write the intervals that you have that are increasing, decreasing, constant, let's go back. Well, I said that my graph actually starts increasing from, this is an X value of 0. So this particular part is from 0 to, that is 3. X value of 0 to 3. Notice that your graph is increasing in that area. So that's my first one. I only use parentheses. So just from 0 to 3 is what you write for increasing so far. Then let's look at our graph from left to right. I notice that I also have another increasing part here. And this is going from an X value of 5 to 7. So from 5 to 7. And those are my only two increasing intervals. Okay, my decreasing interval, we've already said from this point here. Now, I want you to notice something. Notice that your graph is going to go up and to the left forever. So, does your graph really have an end here to where it's decreasing? If I take this graph and I go up, up, up forever, then if I'm reading it left to right, my graph is actually going to decrease from infinity all the way down to that point. Hey, are you good? I'm recording a video for them.
Let me just a quick question.
Okay.
If a kid doesn't turn in an assignment, say a 50-point quiz, they don't take it, they miss the deadline.
Yeah.
All right. What do you record in the grade book?
They told us to put an M, but I mean, I've always put a 1.
Okay, well, that's what we're thinking. We're thinking because now my kids have one grade that's turned it in. It's 10 points. Well,
Yeah.
their average right now is 100, okay?
Right.
So that's what happened 4 to 9 weeks, you know, if they turned in one thing. So if we put down, and we couldn't put down a 1, we had to put down nothing. If we put down a 1 or a 0, that would average out, a 10 plus a 1. And I'm just trying, who would know? That's what I wanted to ask. Who should I ask?
I was thinking that the M worked the same way. Like, even if you put in an M, it averages to a 0.
Is that what the M stands for?
Mm-hmm.
Okay. Is Cindy down this hall?
Yeah. And I think I'm still gonna put in like a 1. I think I'm just gonna keep doing it like I've been doing it.
If I hear different, I'll let you know. That's what we're thinking.
Okay. And then, all right, so going back, we said it decreases from negative infinity because once again, it's going to be all the way up here and it's going to keep decreasing from negative infinity on to 0. So here it stops decreasing and turns, so that's where it stops, is a 0. Then there's another part, it decreases from this x value of 3, that's a turning point, and it decreases or goes down a hill to 5, just from that point there. So from 3 to 5 in that particular interval. That's the only 2 parts where we had a downhill on our graph. So constant part, you've got your flat part. It starts at 7, your turning point changes here, and then it goes flat. So, and notice that it's going to be flat, shows that arrow, so it's going to be flat infinitely to the right. So the only constant interval you have is from 7 to infinity. Only use parentheses, only use x values. Okay, we'll look at one more quickly. So increasing, decreasing, constant intervals. Let's say I have this graph. And I want to find out -2. And I want to find out the increasing, constant, decreasing intervals on it. So let's look at increasing intervals. And decreasing. And any that are constant. The only turning point on your graph, notice the only time in this where it changes direction is here at that point, because it's obviously flat to the left forever. Then it comes to the origin and actually changes to going uphill. So once again, you can draw a stick figure on top of your line, always walking left to right. And of course, that guy's going to be, or girl's going to be walking flat, then all of a sudden they're going to walk uphill. So you see, of course, reading it left to right, always go left to right first. It's going to be constant for this part. So from negative infinity, and remember to only use 0 values. So this will be from negative infinity, and then it stops at 0 on the x. And then it switches gears and it starts traveling uphill for this part, and that is from 0, and then it's going to the right forever. So that would be from infinity, so 0 to infinity. There are no decreasing. Notice that this graph never starts going downhill anywhere. So there's none. Okay, the next thing we're going to look at is what's called local maxima, or relative maxima and relative minima. Local maxima is actually where your graph, so recall the turning points that I just discussed with you. So before I show you the actual mathematical definition, because that looks very beautiful and easy to understand, doesn't it? Let's go back and look at these two graphs that we looked at. Here, when we were talking about increasing, decreasing, constant, do you see all these changing points that I had you highlight where it changed direction from decreasing to increasing? It changed direction from increasing to decreasing. And of course, here was a changing direction. Here was a changing point. Here was a changing point. Okay. So what a local maxima is, we'll talk about it first. Going back to one of my favorite things, roller coasters and amusement parks. What a local, or sometimes you will see it called relative. Relative and local maxima are just points where your graph will top out on a hill. There can be multiple. So as you just saw, of course, where that graph, I had a graph going up, then down. So there can be definitely, you can have only one local or relative maxima, or you can have numerous. You can have 2, 3, whatever. All a local or relative maxima is, it's a point on your graph where it changes direction from increasing to decreasing. Notice on this graph, if I'm, of course, once again, read your graphs from left to right. So I'm going to follow along with this graph, starting here. So this is an increasing part. And then the point which it changes direction is your actual relative maximum. Maxima is plural. But if I'm only talking about one point, I would say relative maximum, where it changes direction from increasing to decreasing. Easiest way to tell you, imagine this is a roller coaster track, if your graph kept going, of course, and this is where your roller coaster is going to top out at any particular hill on that course. So it's showing you here that you change from increasing to decreasing at some value C, which also relates to your X, and then this is your Y value. This is very, very, very important where it says the local maximum is f of C and occurs at X equals C. I'm going to put that to you in easy to understand terms. All this means, if I'm asking you, does the graph have any relative maximum? What are they and where are they located? So you're going to tell me, you're going to say that it has a relative maximum at the X value. So it's going to be an ordered pair. Its location is at the X value. You would tell me the actual relative maximum value is your Y value. Because think about it like this. It's like if you were on the ground, let's say that we're looking at a roller coaster track from the side, okay, in two-dimensional form. You would tell me, okay, well, it tops out at a hill 50 feet into the track. So let's say that was 50 feet into the track. And then you would say that first hill height was 100 feet, whatever, something like that. So you would say it's got a relative maximum point, 50 feet, at 50 feet into the course, but the actual relative maximum value is your height. So think about that, just gives like horizontal location, and this gives your vertical height of it. So this is your vertical, or we could say vertical displacement if you would rather. So vertical height or displacement. All right, and that you'll see this will be a little bit easier to understand in just a second. All right, we're going to look at a local minima. A local minimum, so just as a max is where a graph tops a hill, so to speak, a local minima or relative minima, relative minimum. Minimum is singular. The minima is plural in case it has more than one. And all this is similarly to where a maximum was topping a hill, a minimum is bottoming out. You know that when you're riding a roller coaster and you go down the hill and all of a sudden it hits that bottom and pulls you back up and you feel, sucked to your seat and feel that gravitational pull. Think about that as being a relative minimum. And I know the next time that you go, and if you ever ride on a roller coaster, I know you're going to think about math and all of that, right? Yeah, sure. Okay. Your graph changes direction from a decreasing part, reading it left to right, to an increasing. It is that point where it changes, a local minima, the point at where it changes from decreasing to increasing. So it's going downhill, your person's walking downhill, and then all of a sudden they start climbing the hill. And that point where they change direction is a relative minimum or local minimum, minima plural. Once again, very important. You would tell me, okay, well, if I was hiking this path along the mountain ridge, I changed direction, we would give the horizontal displacement. You would say, well, a mile in to the course, or a mile into my path, I changed direction at, 1,200 feet in the air. So the X value always gives the location or horizontal distance. So you're going to say at, and read your directions very carefully in your homework, at your X value, and the actual relative minimum value is your corresponding Y value, because that gives your, once again, that gives your vertical height or distance. In this, all right, we're going to look at some examples of finding the local maxima and minima. So find the local maxima and local minima from the graph of a function and determine where the function is increasing, decreasing, or constant. So in 1.3 homework set, you're going to have some problems just like this. And if you will notice, of course, find the local. So we're going to read your graph from left to right. Notice, of course, it's going to go up and to the left forever. and then there's no gaps in the middle, and it's going to go up and to the right forever. You're finding, so let's go ahead and highlight all of our points where my graph actually changes direction. So notice if I'm reading it left to right, it's coming down, 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 and then it does bottom out. So here is a changing point. Now we know that those changing points are called maxima or minima. Notice once again your graph changes direction here as well as here, and then it goes on forever. So we have to determine what these 3 points are. Are they maximums or the top of a hill, or are they minimums at the bottom of a hill, so to speak? In part A, you're asked, does your graph have any, or at what numbers at, very important, at is location or X values. At what numbers, if any, does f, this function, have a local maximum? So we're trying to see, are there any points where this graph tops the hill and then goes back down? Are there any points, in other words, where it changes from, we're looking where it changes from increasing to a decreasing interval? So if I look here, I've got this, notice that my graph, let's go back and list increasing, decreasing, and constant first. Well, you definitely do not see any flat portions of your graph. So there are none. You do not. All right, so then we're going to look here from this part of your graph. It's decreasing. It's decreasing from here to here, and that would be from negative infinity. Once again, we always use x values, and we always just use parentheses for increasing, decreasing, constant. And then it stops decreasing at -1 for that part. And then here it is actually increasing from -1 to an x value of 1. And then it goes back to decreasing here. And that x is 1, 2, 3. Then it picks back up, starts increasing from here to here, and that would be from 3 to infinity. It's going to go right forever. So that's our increasing, decreasing, constant part, but we're going to use that to help us find our maximum. And they didn't ask for minimum here, but we're going to cover that as well. Okay, so let's look. All we're looking for is maximum. So we're going to pick out, notice for this particular graph, this is the only point we have on our graph because we don't know what it's going to do here. We know that this looks like it's going to go up forever. This definitely looks like it's going to go up forever. So the only point so far we have on our graph where it changes from increasing to decreasing or tops the hill is at, you've got this point which is 1, 2. So we do have a maximum point. You've got a maximum point at 1, 2, and we use the x value to give, we use the x to give location. So we'll say it's at 1. That's all you have to say. If you're telling me where it's at, you're just going to use the x coordinate. So 1, and then what are the local maxima? That's where you tell me the y value. So what are they? This would always be your y value. It's at the x. The value of it is your y coordinate. So you would say 2. Those simple answers, you feel like you've gone back to elementary school, huh? Just getting to say 1 or 2. You don't get to do that much in upper level math. Okay, really quick. Let's go ahead down at the bottom, and I'm going to go ahead and show you any relative minima. So notice that you actually have two relative minima here, because that's where a graph bottoms out, or that's the bottom of your roller coaster track, or that's where your person, if you draw a stick figure on your graph, would change from walking downhill to walking uphill. So relative minima, all right, you've got two of them. This first order pair is at negative 1, 1. The second order pair is at negative 3, 0. So you're going to tell me that it's at, you've got two of them. 2 at negative 1 and negative 3. Then you would say the values are 1, your y, and 0. Because you're telling me the horizontal displacement, and then you're telling me the vertical height. That's actually a minimum value, like how far down or up it goes. Okay, actually we just covered this on that last slide. Forget about that. Okay, I'm going to go ahead and close out this video. The next video that I do of we're going to continue another one of 1.3 that's going to have difference quotient, even and odd functions, and symmetry on it.